invitation. I hope you can see the screen. I will keep this like this. Like, I hope that won't be too bad with the title there. It just makes it easier for me to also see you. So if you have a question, feel free to either use this raise the hand feature or just speak up. I think we are kind of few enough people that it's easy for me enough to just stop, and I'm happy to be interrupted if it makes sense to clarify parts I don't understand. Okay, so thanks for the invitation. As I said, I would have been very much like to come to Canterbury in person, but like this virtual visits are also nice. Yeah, I've been in Scotland for quite some time now. Like, I used to did my PhD in Germany and then did a postdoc period in Edinburgh and was a lecturer until the summer in Glasgow University. And I'm now back as a lecturer at Edinburgh University. And I work kind of on the interface of systems and programming languages. So I usually say I do programming languages and compilation. And now my job title actually says that I'm a lecturer in compilers and runtime systems. So I'm kind of right in the kind of at the boundary of systems and programming languages. And I use quite a lot of functional programming techniques and methods in kind of a classical high performance or systems setting. And this, what I'm going to talk about today, is mainly based on work that I've been doing with a couple of my PhD students, some of them named down here. And then my former, like as collaborators, my former PhD supervisor in Münster and a colleague, Ornella, from Glasgow. And this is mainly based upon a paper that we presented at ICFP this year, which is like was accepted as a functional Perl, and we pitched this kind of as a nice way to use functional programming to design a kind of domain-specific compiler for achieving high performance. Okay, and I think in this setting, when we talk with kind of programming language people, sometimes we need to emphasize what we actually mean by high performance and why we actually care that much. Efficiency to a degree, which sometimes seems really crazy, kind of how much we care, but the often doesn't come from us, the people writing kind of compilers and doing like advanced optimizations, but it comes quite often from the application domains and the applications we want to run today and tomorrow on the hardware we have today and tomorrow. So if we think, for example, about how expensive it is to train a machine learning model nowadays, then this is a tweet from June, summer 2019, from like a machine learning person saying like, holy crap, it costs $245,000 to train the XLNet model. That's a model in natural language processing that beats the BERT model. And he estimated this based on using 512 tensor processing units of specialized hardware for 2.5 days at $8 a TPU. And if you recompute this in terms of carbon spent and not in terms of dollar spent, then my PhD student did kind of the math and said that is the equivalence of you take a car and you drive from the north tip of Finland all the way down to the south tip of South Africa. And that's the carbon emissions you emit for training this machine learning model. Okay, so if we now think that this might not be the only model we want to train, we might want to, like the time for developing this model, the cost in terms of energy, in terms of bit, we might want to think about, if we think these models are important, and a lot of people currently think they are, then we might want to think about how can we optimize them more, okay? And a trend we can see kind of picking up on this is that we see kind of a large boom of specialized hardware. So we see here different types of hardware accelerators, which like different features, which pop up and offer different performance powers at different, or performance based on performance like commitment. We get different performance out of this. But the question obviously is who's going to program and optimize for all of these new hardware devices coming out? Like if we have like hundreds of different hardware devices, like who's going to optimize for all of these different devices? So we need somehow automation in this space. At least that's kind of, I think, a pretty clear message from my side. Okay, and if we think about how do we usually traditionally think about optimizing software, so if we think about performance-sensitive code, right, then we quite often rely still on some form of compiler heuristics. So we have like here the Clang compiler, which I guess is like an industry standard compiler. When we give them the -03 compiler flag, it says like, we enable all the optimization that we can in an attempt to make the program run faster. So it's kind of a little bit praying to the performance gods of like the performance like turns out fine. Obviously these compiler heuristics, they're optimized somehow for average cases, and they might not necessarily be optimized the best way for the performance sensitive code or for the hardware that we have in mind or that combination. Okay, so compiler heuristics are really kind of making most of our programs faster, but maybe not our machine learning model we really care about. The other option we obviously have, and we have picked up for quite some time, is to say we just write low-level code. Okay, so instead of writing code that we actually understand and that works well and that we can easily port from one computer generation to the next or from one hardware architecture to the next, we suddenly express code by writing like hundreds and hundreds of lines of detailed instructions how a particular hardware architecture should execute our code, right? And that really pays off. So sometimes here on the left, like the textbook matrix multiplication, and then we have an optimized matrix multiplication on the right, we get like a 30 times of increase in lines of code, right? I mean, maybe an even larger increasement in complexity of understanding what's going on. But we do get like orders of magnitudes of performance gains by better exploiting the hardware that we have underlying it. So low-level error code is kind of the way to go in a lot of domains, but it's error-prone, it's hard to debug, and it's specific for a single device or architecture. So that means next generation, next hardware comes along, and we have to kind of start from scratch quite often, or at least adapt significantly. So kind of a space in between here is now, or kind of a newer trend, is a family of compilers, which are kind of domain-specific compilers in some sense. So they don't try to be able to compile every piece of code that computes arbitrary stuff. So for example, the Halide compiler is a compiler for image processing applications, or the TVM compiler is for kind of machine learning. And these more domain-specific compilers, some of them, or in fact actually all four of those, they introduce kind of a separation between what they call the program, which is a description of what we would like to compute, okay, and then a description of how the compiler should make that happen. And that is what they call a schedule, okay? And this separation sounds great because it means the next hardware generation comes along, we change the schedule, we keep the program, everybody's happy. Okay, so that's kind of an appealing design in general. But what's broken or what's wrong with this designs that we have so far? So good points, clear separation between computation and optimization, and we have a lot of control how to perform optimizations. Okay, but that point here didn't, unfortunately, the slide didn't come across through. This was supposed to build up. Anyway, I make kind of my points here nevertheless. Okay, so one of the problems we see is that we actually share in our program here, right? We use the same variables like this X here, right, as we're going to refer to directly in this program. So we have kind of no clear separation actually in between this program and this optimization. In fact, they're often written together and are fairly closely intertwined, okay? And a lot of these, and even further, in the manuals of these compilers, when we want to express certain advanced optimization, we are often forced to actually change the program, which is kind of missing the point of saying we have a description of our computation, and then we want to do optimization and say, yes, but for this advanced optimization, you have to change somehow how you think about the computation fundamentally. And so we have to change how the program looks like. So that's like definitely a property we don't want to have. Okay. Then we have a lot of these kind of detailed detailed abstractions, like we have here a section called update, right, which has a kind of, in the description, a very kind of dubious semantics in the sense of like, it isn't clear what updates or what it does, okay? And quite often, actually, these optimization schedules, they talk about how the compiler thinks. So when we have here something called unroll, then we talk about unrolling a loop, but in my program, there is no loop, right? So what do I actually unroll? What does unrolling here mean in that context, okay? And then the last bit is that all this functions or operations that I can perform in the schedule, they're all built in and pre-exposed compiler optimizations that the compiler writers thought are worthwhile to exposing. So stuff like here, splitting, which corresponds to kind of tiling a loop, unrolling loops, spreading them across GPU threads, and so on. So we have like a fixed set of optimizations, which we can't easily extend if a new hardware generation comes along. Okay, and what I'm trying to argue in this talk is that we should somehow aim for more principled ways to describe and apply optimizations. And I essentially say, like, let's try and use functional programming as one way to model these optimization schedules on its own right. Okay, so I'm setting out 5 goals that I would like to achieve for this. Okay, so the first goal is I want to clearly separate the concerns of computation optimizations. Okay, the second goal is I want to facilitate reuse, not just of computational parts, so that I write kind of a library function that can appear in a lot of different contexts, but I also want to reuse optimization ideas and optimization parts that might apply to different applications or to different hardware components. Okay, a crucial aspect is that I want to enable what I call composability. So I want to be able to take small bits and pieces and plug them together in a well-defined way so that I get like a useful larger building block out of this. And that should really apply not just for computations where we have the idea of composability, like by saying, let's compose 2 functions together, but I want to compose optimizations together. Okay, and I want to describe optimizations as building blocks of smaller things. Okay, I want to allow reasoning about how optimizations change my program. Okay, and particularly, I want to have no surprises. So I want to be explicit, because that's one of the other aspects that these existing compiler frameworks do. They have implicit behavior that is not really controlled by those optimization schedules. Okay, and fundamentally, somehow, we argue that to achieve kind of this more principled high-performance code generation, we should somehow consider computation and optimizations of equal importance. And currently, in the schedules, we have a fully fledged language for describing computations and a pseudo API or an API for with limited capabilities to plug optimizations together. Okay, and I want more importance on the optimization side of things. Okay, and as a consequence out of this view, we design what I call a strategy language, which is a programming language on its own to describe program optimizations. And we want to build this kind of with the same standards as a language that we use for describing computations. Okay, so that's kind of my setup here. Okay, so what do we set out now to do? So we say we have a compiler down here, okay, and the compiler takes 2 things. It takes what I call a program, which is a high-level program that is not specific to the hardware we are going to try to run it on. And then it takes this thing, which I call an optimization strategy, which is a description how the program should be optimized. Okay, and the crucial bit is that the compiler doesn't know anything really about what the strategy tries to achieve or does. It just takes the strategy and applies the transformations described in it, which are described as a composition of rewrite rules. And we receive a low-level program that is now all the optimization decisions being encoded in it explicitly. And then we generate code from it in which we can execute. Okay, and this entire stack here is functional in nature. So these are all functional programs, and then down here it becomes imperative. Okay, so what does a high-level program look like? This is a description of a high-level program describing a matrix multiply. Okay, so we have here, like from functional programming, well-known operators like a map, right, or reduce. and we describe with these patterns a computation. And these patterns are chosen in a way that they allow for a wide variety of implementations, right? So I can parallelize and map easily. I have ways to parallelize or reduce, right? And apply different optimizations like vectorization or whatever. And then on the other side here, we have kind of the new thing, right? And that is what I call a strategy. And this is here a composition out of smaller rewrite rules that describe individual program transformations. And the crucial bit here is that we have a language where we compose them together so that they describe an entire transformation of this program on the left. Okay. Okay, so the interesting bit which I will most talk about is this elevate strategy language on the right side. Okay, so what is the crucial idea of this elevate strategy language? Okay, so in this language, a strategy, which is essentially a program transformation, is described or is encoded as a function. Okay, so what does this function look like? This is not an arbitrary function, but it's a function that has a specific type. Particularly, we call this function a strategy if we have a program type P going in, and we will turn this into a rewrite result of P. And the rewrite result indicates either I give you back the rewritten program or I return your failure case. So this is kind of like a maybe type, if you'd like, right? So kind of a monadic maybe type, which means I enable composability using kind of, in some sense, standard functional programming notions, okay? So the most simple example that I can give for a strategy is a rewrite rule where I have a fixed pattern. So in this case, what I say is I have my program P. I pattern match against the shape of this program. So this is kind of a pattern describing the AST of my input program. And then I'm replacing this with a program AST of the output program. Okay, so on here, kind of the yellow boxes, they are described kind of computation, or here on the left, AST's representation of computational programs. And the blue box that's the strategy. That's kind of the program transformation. Okay, if I don't see a program that has the shape, then my strategy will just fail and say like, I don't know how to rewrite this program. Okay. Meaning that what this map fusion strategy does is it takes a program of that shape and gives me back a program of that shape. Okay, so it's really kind of an AST transformation from one to the other. Right, but the crucial bit by reformulating this as a function of this type is that we can think about composing these now together. Okay, meaning I can define a sequential composition operator, which takes a strategy F, right, or the first strategy, a second strategy, and then it will itself be a strategy, meaning if it takes the program P, it will first apply the program to the first strategy. And then we have here this kind of monadic combinator saying like, if that is successful, then I get back a rewritten program Q, which I apply to the second strategy. If the first strategy fails, then the entire sequential composition fails. Okay, so saying essentially just, it's kind of like, this is literally like you would define function composition in some sense, okay, but accounting for this failure case. And then we can define other combinators. For example, we have this left choice combinator that is taking two strategies, and it will try to apply the first strategy, and it will only apply the second if the first fails. So it will choose the first, but if that fails, it will try the second. Okay, that's why it's called left choice. And then we can, using these, we can build up other combinators like this try combinator, where we say, give me a strategy S, I will try to apply it. And if the strategy fails, then I will do nothing. And we can define this in terms of this left choice. Okay. And similarly, we have a repeat strategy, which says repeatedly apply the strategy until you fail. And that's essentially what this repeat does. So it applies a rewrite strategy until the strategy fails and is not applicable anymore. Okay, so these are now combinators. So I can compose my strategies together in some way. So far, I've now talked about how we can encode in this framework kind of individual program transformations. I've said how we can compose multiple of them together, but I haven't really talked about where we apply the strategy. So I have my entire program, like how do I actually determine that I want to apply this strategy to this subpart and not to this other part, right? So to this grouping of functional patterns, okay? If we, for example, consider this program here, okay, which I've named 3 maps, where you apply essentially map like H first to XS, then G, then F, okay, and that is the AST out of this. And I have this map fusion strategy that we saw before that takes 2 maps and fuse them together into a single map, okay. I have now 2 choices. Do I apply this to the second pair or the first pair of these maps, right? And they are like just equal. How do I actually make this happen, okay? If I, and for that we can introduce what we call traversals, which are again strategies. So they are just functions like the other, okay? But they now say for this body traversal, for example, I say, if I see in my AST a representation of a function node, like a lambda node, then I will apply my strategy to the body of this lambda node and will rebuild my node around this. Or I will, if I see a function application node, I will apply the strategy to the function application node and then rebuild a function application node. Or if I see an application, I will apply to the argument. So I can kind of, with the traversals now, start to navigate my functional program. And I can, for example, say, please apply my map fusion strategy to the body of this function, which would apply it to this entire thing. So it would fuse the outermost ones, okay? Or I would say, no, go to the body and then jump into the argument, and then it would apply to these 2, map G and map H, okay? So this is obviously a tediously precise way to describe where to apply stuff, okay? And you don't want to do this, but sometimes you want to, I mean, in general, I guess you don't want to do this, but sometimes you want to have this ability to describe where stuff goes that precisely. We can generalize these traversals with kind of what we call basic traversals or kind of generic traversals. And this is, and I should say this, a large part of our design here is built up on prior work on kind of rewrite languages, particular a language called Stratego from Elko Visser and colleagues. And he proposed, among others, back then that you have kind of 3 traversals, which are having kind of the all-one sum traversal, saying if I have an AST node, should I apply the strategy that you give me to all my subnodes, and they all have to be true, or they all have to be successfully applied to one, and if one fails, I will try the next one, and then the next one, and the next one, or to some, which meaning I try to apply it undeterministically to multiple, okay? And we don't actually make any use of this undeterministic sum part in our setup. And using these, we can now define traversals that might sound a little bit more kind of tree traversal-like. So we can say do a top-down or bottom-up traversal of my program representation by combining these generic traversals with some of the other combinators that we have seen before. Okay, and that is in some sense just a clever use of functional programming to know how to design these basic APIs. Okay. A crucial traversal primitive that we care about is the idea of normalization, which means we want to apply a given strategy to all possible subparts of our program until we can't apply the strategy anymore. And one way to encode this is to say we're going to repeatedly traverse our AST until we can't apply these top-down traversal anymore. Okay, and using this normalization, we can, for example, in the lambda calculus setting, apply stuff like we can apply a beta-eta normal form, which is like a standard normalization property in kind of these program representations, functional program representations. Using all of these small building blocks, I've now shown very small building blocks, right? We can express really useful high-performance optimization, like high-performance optimizations, like, for example, loop tiling, which is a traditional like a traditional optimization that is very important if you want to achieve high performance, because it exploits locality of data, which means you get a better cache performance and kind of can exploit kind of this locality effects. And we can define here, what I show here is kind of an arbitrary dimension tiling. So we can do 2, 3, 4, 5D tiling with this single strategy, which is kind of a recursively defined rewrite process. Okay, and the crucial point for us here is that in the schedule that I showed at the beginning from Halide, they have a tiling program optimization in there, but this is really baked into the compiler. Okay, and this is 2D. They can't do 3D tiling easily without changing the compiler design. This here is just a composition out of very simple rewrite rules, and the compiler has no clue that it's actually doing tiling when it's applying the strategy. It's just applying these program transformations one after the other to it, meaning something like tiling is completely designed outside of the compiler and not inside the compiler, which I think is a really important property that we have, because it means next generation of hardware comes along, I want to have a different tiling way to do tiling or different other optimizations, I should be able to express this. Okay, so we've actually applied this, so we've implemented this in a framework in Scala, largely implemented, and we compare here against, so we did kind of a case study where we compare against one of these compilers called TVM, which is a compiler used in kind of deep learning applications. And they have a tutorial where they describe how do you optimize a matrix multiply on a CPU, okay? And they have kind of a description of matrix multiply, and then they have different schedules. And at some point, they actually have to change the program description to enable more advanced compiler optimizations. And then, it really pays off for them because they get a performance boost of like over 100 times from the naive baseline version down to the version that actually parallelizes it, uses vectorization and other instructions, including tiling. Okay. And for us here, it's not that much that we are interested in the absolute performance, but what we were interested in, can we reproduce these versions, these optimizations that are baked into the TVM compiler, and can we encode them as functional transformations based in this Elevate strategy language? And when we then have applied them to our functional program, our functional matrix multiply, when we then generate like imperative code from it, what is the performance that we can get using that way? Okay. Meaning, we have now here a description of on our side on the left of the functional description of what matrix multiply looks like. So that was literally the input we gave to our compiler. Like, this is a matrix multiply which has map dot product, and then I'm happy, right? Textbook matrix multiply. And in the TVM world, they describe this here. You can see this in line 5, 6, and 7. They describe here also, they say, we have here a description of, we do the sum here is essentially the reduction of the dot product, and then they apply this here for across these two axes, and essentially that is the description of matrix multiply they start from. And on the TVM side, they say, oh, create me a default schedule, and they make some optimization decision already at that point. For example, they will fuse the kind of map computation that goes on here into this bit, which we describe now explicitly in our composition in our schedule, right, or in our strategy. The crucial bit for us is we have a clear separation of concern, right? We are explicit about what our optimizations are, and these are described purely as compositions of these lower building blocks, these smaller compositional building blocks. Okay, when we start to compare other versions, for example, this is here a version, this loop permutation version, which was, this middle version here, okay. For that, the TVM applies, for example, this tiling rule, okay, which we have seen, which we replicated using this tiling primitive that I showed briefly. Okay, again, user-defined and not built in. And we were able on our side to now give this version a name and say, like, this is the loop permutation version, okay, which we could then easily reuse when we built up and had further optimizations that we built up on top of it, okay? Where, for example, for this particular example on the TVM side, the step from this loop permutation to the next optimization required a reformulation of the matrix multiplication. So they had to actually, you see this up here, they had to introduce an intermediate result, this PB, which they computed before they combined this together. So they do a pre-computation where they packed some data together, which you then access in the other bit. So they had to change their description of the computation to enable more advanced optimizations. And that, I think, is like a real problem with kind of this with TVM-based approach, if you'd like, which on our side was really not required because we could build up one step of this, on step of this, on step of this. Okay. Okay, so does this actually scale? Does this actually work? Okay, so I have two graphs to show for this. Okay, the one here is, the first graph is here. It's just counting how many individual rewrite steps did we actually apply to turn the base matrix multiplication, so the map dot product based version, into a low-level version that had all the optimizations applied to it. Okay. And we are counting here the number of successful rewrite steps, meaning when a rewrite rule actually applied and did a program transformation, not when the rewrites individually failed. Okay. And we see that for very quickly here, we apply like tens of thousands, like 40,000, 60,000 individual rewrite rules to apply these program transformation, to do these optimizations. Okay. Which means what we read out of this is like, this really scales, right? So we really are not at the point where we apply 2-3 rewrite rules manually and it somehow magically works. No, we apply tens of thousands of rewrite rules where we can't follow necessarily each individual step like easily, right? But it works in a practical sense that like we need less than like a couple of seconds to apply these optimizations. Okay, so this is not like a problem where we do kind of a very computational intensive process here. Okay, so we're happy with this. It scales to kind of these type of optimizations that we aim to express. And then performance, okay, and this is now kind of a little bit of combination, because here we have the rewrite-based approach of turning kind of the, like applying something like tiling and so on and so forth. But then this also includes our code generator, which turns kind of a low-level functional program into into CPU code, imperative code. And that is this RISE part, okay? But if we plug them together, then we can see they achieve very close performance compared to the TVM compiler. In particular, what we observe is that we see the same trend, like the same optimizations, right, that were beneficial on the TVM side are also beneficial on our side, which is kind of what we wanted to observe, right? So we see essentially that we are able to express the same set of optimizations that are encoded and baked into the traditional compiler in a much more flexible setting, and that's what we're hoping out to set out here. Okay. Yes, if there are questions around this part now, then I'm happy to take them maybe now. I have a little bit more stuff where I talk about kind of some more advanced directions we go on with Elevate. But if there are questions, I'm happy to answer them now. Justus.
Yes, I was just thinking about like since your strategy is a little more general, right? Like they're more it's a more general way of describing the same kind of optimization that like TVM would do. My question would be: is it harder to maintain something like this? Because when you're less explicit about like the variable you're manipulating or whatever, that that gives you generality, but on the other hand, it's sort of it's like, let's say your actual program changes, like right. You have to keep that sort of the two have to still line up somehow.
So I guess you have kind of the question of like, if I have now this setup here where I say one program, one optimization strategy, how robust is kind of the strategy if I change stuff in the program? I guess this is one way to phrase it. So if I change slightly the program, I'm not sure if I've captured your question.
Yeah,
right.
kind of. So yeah, sort of if I change my algorithm, how do I make sure that the strategy still fires?
Right. Okay. So there are different ways how you can encode these strategies, right? So I showed some very almost representation specific ones to say go into the body of a function and stuff like this, right? A lot of these strategies here, they are, so what we have tried to design here is we have designed something like tiling, right? Which really has kind of some idea about how the input program looks like and how it turns it. So it expects a certain nesting of map patterns, for example, which corresponds to a nesting of loop nests, okay? And we have separated this out from the second part, which we have described here, and I haven't talked about this, which is these at notation and then these outermost map nest 2. And that is kind of our attempt to have a declarative description about where we would like to apply these strategies, okay? And these here, they are a little bit more generic. So they use these generic traversals to say, traverse my AST, find me a certain node that has a certain, like find me the first map, for example, or something like this, right? Or find me, in this case, the first nesting of 2 maps, okay? Meaning, if I change this program slightly and I do some computation before the matrix multiply, right, then I would still be robust enough with this description, okay, to say, oh, skip this computation and then apply it, okay? For example, if I would transpose my input or something like this, okay? But obviously, in at least this formalization, the entire idea is that you have the ability to specialize your strategy for the particular program, okay? So it's in some sense up to you how crazy you go with whatever strategies you apply and how generic or how specific you make them. So it's very easy to write a strategy that is very generic and says, try to vectorize every reduction you find, okay? But you can also write a strategy which says, skip the first 2 reductions and only vectorize the third. And now it's essentially your choice or your design point to say, what do you actually want to do? Do you want to have the control, but then it won't be as portable, or do you want to be a little bit more flexible, and then you might have a little bit of leeway on if the program changes slightly. Okay.
Okay. So you does that mean you could do something like you say, I have this generic strategy, and then you sort of have a combinator that says, I expect this to be applied at a certain point. Like you say, well, when I hit this program point, from that point on, it should fire this strategy. Like, can you
yes,
sort of
so we have things which we call predicates, for example, which you can think of as this is a strategy again, which fails if it's not true, and if it's true, it succeeds, but it returns you the identity, right? Okay. So it says like. And then we have, like, for example, here this is app, is map. These are kind of predicates, right? Meaning, and then this innermost is a traversal which says, if I find exactly this composition of nodes, then I will apply this vectorization strategy. Okay, so you have kind of a more or less, still fairly low level, but a little bit more declarative way to describe what composition of AST nodes in some sense you care about here. Okay.
Okay. Cool.
Cool. Okay, I give a very brief, if there are no more questions now, I'm happy to leave a little bit of room, right? I will give a very brief overview now on kind of some more recent work we have done kind of with the setting. And that is, I said, when I kind of set out on my quest, I said, like, I want to treat the computation and the optimization strategy as kind of as equally important, and they should both be languages on their own right, okay? And if we think about languages, one crucial thing we would think about is to say, oh, they should have somehow types who help us to, like, write correct programs, or in this case, maybe write correct strategies, right? But there are also maybe types that might be useful for other purposes. Okay, so you can see types as propositions when you try to prove correctness for certain things, right? So using kind of propositions as types, or Curry-Howard, right? You can see a types of specification for program synthesis and all sorts of other use cases, right? So we have set out to design a type system for the strategy language Elevate, okay? And for that, we use a row polymorphic type system, okay? And I'm aware that I have like 12 minutes left, so I will be a little bit quick on this. But the idea here is, so we have kind of rows as a concept. So row polymorphic type system means we kind of want to generalize, or one way to see them is kind of they are a generalization of record and variant types. So like if you have like a record or a struct, right, or you have a variant type, you can observe that they both are in some sense just a sequence of label type pairs. And that's exactly what a row is. So row is either empty or a label type pair composed with another row. Okay, so that we can, for example, here say the point x, y, z can be described with this construct, okay, which is kind of a struct or record type, which has this row in it. And this is a variant type, which says the color is either red, green, or blue, okay. And the like one of the ideas or one of the things that is kind of crucial to row polymorphic type systems, or type system that says I have rows as my way to think about records and variants, right? And I use polymorphisms, so type variables, okay? And one choice here is to explain using this mechanism how we can, for example, make a point that has the components x, y, z, and a color fund point, which has like x, y, z, and on top of this a color, right? How we can make these two types compatible, okay? And you might think we could use subtyping, for example, to explain that the one can be seen as a subtype of another. But in a row polymorphic setting, what we would say is we would have a row variable here, which says that we can extend this row. So we can say, oh, a point is x, y, z, and then some other stuff that I don't know about. And when I want to make these two types compatible, I can instantiate this row variable with this, for example, this row here to say, oh, they are compatible because I can find an instantiation to make these compatible. Okay, so this is kind of a very brief introduction kind of on what rows are and row polymorphism is. Okay. One interesting bit for us is, and I skipped this bit, is like that we can use a row polymorphic, or we use a row polymorphic type to represent our computational language as types, like as a type at the type level. Okay, so this is a recursive row polymorphic variant type where we have kind of all the usual suspects of functional lambda calculus setting. Okay, and that means I can now write an expression like this. Okay, I can desugar this, and then this looks maybe like this. Okay, awfully long and complicated, but it's the same thing. And then I can infer a type that reflects essentially the structure of this program in its type. Okay, so this is now a variant type which says either it is exactly the program shape that I observe, okay, or, and then here's the other stuff, it could be something else. But in this case, it's kind of like, it's exactly the type that you have observed, okay? And the interesting bit is that we can now use this to have our strategies that we saw before to give them more interesting, more useful types, okay? So where before the strategy was the program P goes to a rewrite result of P, and the P essentially was just saying, I'm an AST, right? I knew nothing about that, what the shape of my program that goes into or comes out of my transformation was looking like. So what this strategy type now tells us is that a program P of shape P1 goes in, and I get a rewritten program of shape P2 out. Okay, and I can capture what my program transformation is actually doing to my program. Okay. A concrete case of this might be here on the left-hand side, I see our map fusion rule, okay, and then I see a complicated infer type on the right-hand side. If I sugar this a little bit, that becomes easier to read, okay. So the idea here is that I can write my rewrite result here, okay, sorry, my map fusion rule. So I turn map G, map F into map of FG, okay? And I can infer a type for this which says my input is a program of the shape map G, map F, XS. And my output is a successfully rewritten program that has exactly this shape, okay? But that now happens at the type level, right? There's like, I don't need to know anything specific here, right? The GF, they are variables, they can be anything, okay? And in the setting here, they just become type variables on the right-hand side. So they just become polymorph, right? And I can capture here essentially now what this program transformation is, which means I can think about how can I actually, when I compose multiple strategies together, right, can I statically now reason about what this composition actually means, okay? And I skip briefly this and come back to the slide. And yes, we can actually do this. So if I sequentially compose now my programs together, I can now automatically infer a type that tells me that my input program must be a composition of 3 maps, and my output program is just a single map which has them composed together, okay? And I can essentially observe statically already before applying this, if I would apply the strategy and I see a program that has this input shape, that's what I get back, okay? And we can define using this type system the combinators that we had seen before, and we can statically reason about some properties already just on their own. So for example, I have an identity like strategy, which just returns always success. I can see that in the type, right? It will always return the program unchanged. I have kind of a fail strategy that always fails. Well, that always fails. I can see this on the type. It must be failure, right? If I see my sequential composition here, I can see that I put a P1 in and I get at the end out whatever spits me the second strategy out. That's my type here, okay? And then for the left choice, for example, I can see that if I fail, so kind of this case here, like I can see I can always succeed, but if I fail, that depends actually on if my second strategy will fail or not, okay? Meaning one consequence out of this, I can see, for example, statically that if I have these try combinator, this can never fail. Like this is something that I can statically see already, that this try will always succeed in some way or another. Okay, so we've designed a type system that looks currently, if you like, I mean, and looks like this, but I think about this like this, which tells us statically useful information, okay, and prevents us composing strategies together that really statically can't go, okay? So if I have a program that rewrites me into a shape that another strategy expects a different shape, then I can't statically compose them together. I get a type error if I try to do that, okay? And a use case we see besides these safe compositions in the future is that we would see this kind of as a stepping stone to do other useful things with this language. Particularly, can we use kind of this formalization to verify the correctness of program transformations, okay? So where we see now in a kind of dependent types of proposition setting, I could say that I have my program transformation. I can specify this now as a type, okay? And if I find an implementation of this, I can say like, oh great, I can actually provide an implementation of that. Okay, I can do that program transformation. Or could I use types as specifications and then use program synthesis techniques to actually try to automatically synthesize program transformations? So where I give kind of almost by example, this is the shape that goes in, this is the shape that goes out. I give you a type, like a function type. Can you find me an implementation that makes this type true? So can you find me an elevate rewrite sequence that actually is then like satisfies this type, right? Meaning that fulfills this program transformation. So that is kind of an advanced thing that we would like to be able to achieve using this formalization, okay? But that is clearly future work, right? So we have written up kind of this type system, and this is currently under submission. And I'm ending here, by the way, so just for this, right? But these kind of advanced future directions, I thought it would be interesting to mention them here, particularly if there are interest from other colleagues in that domain. because I'm very much not a person working in program synthesis that much, right, or having a super strong background in verification, but I think these might be interesting applications for us to think about kind of compiler transformations or program transformations in a different setting using this setup. Okay, and I will finish here, and I recognize we have only 3 minutes until 4, but I'm happy to answer any questions.
Great, thank you. Yeah, questions.
Thanks, Michael, for that very nice talk. I had a question about the kind of programs that you can write and optimize in this setting. So I was wondering about like stencil computations and being able to do, I mean, you mentioned tiling optimizations, but I think there's some other kinds of things like trapezoidal kind of optimizations and things that people do in that space. Is that within the remit of this kind of thing?
Yeah, so I'm kind of always publishing kind of in the PL or in the systems conferences, and I'm kind of always switching forth and back in some sense. We had a paper on the more systems side where we looked particularly at these stencil computations, and we kind of found a way to decompose them and express them functionally. So you kind of you reuse the map pattern as the only pattern introducing data parallelism somehow, and you describe essentially how you compose kind of these local neighborhoods, which kind of where these stencil computations work over in a way. And we have multiple papers that talk about how to optimize those. And we apply optimizations such as tiling. And we have now like an upcoming paper that talks about some more kind of lower level optimizations where there's certain vectorization ways you want to treat your data, right? We have, for example, expressed also in this framework separability of convolutions, right? So which is a domain-specific optimization that you don't want to bake into a compiler and don't want heuristics to apply to it. But if I know precisely that my composition is separable, then I can now in this strategy, in this elevate strategy, say, oh, please apply the separability rewrite, and that would then perform it, right? Which is in general, you can't in general do that, but depending on the weights of the convolution, you might be able to do this and get performance out of this, right? So yes, we have done this. I don't think we have done kind of crazy, like you mentioned, kind of some more advanced, like shaped, like weird shapely convolutions. Those we haven't expressed yet, and I think that would be interesting to see. But we have looked quite extensively on convolutions so far.
Cool.
Thanks.
There's a question on the chat here from Mike.
Yeah, I'm not sure if I can see the chat actually, to be sorry.
So he's asking, don't know if this was mentioned, I missed it, but what guarantee do you get about programs after applying rewrites, even if you don't guarantee their fully preserved semantics? Do you guarantee the resulting program is safe or type checks or anything like that?
Right. Okay. So we have so in our current implementation, right, we don't have a proof for that the rewrite rules are semantic preserving. Okay, but we have looked with some students into proving the semantic preservingness of some of these rewrites externally using ACTA and other settings. And I think the ultimate goal might be to say, well, you specify them in ACTA and then you generate the Scala code only if they actually type check or something like this, right? But the transformations we perform are in a functionally language, right? And before we do code generation at the low end, so from functional to imperative, these programs, they have to type check again, right? So they have to type check, and then we turn them into imperative programs. So ideally, the program should be semantic preserving, type preserving, right? But currently in our implementation, we don't check that. That's kind of, I guess, the answer is you might have expected, I guess. That's the system side of things, our actual implementation, right?
I'm just curious about another thing. There's no mention of any kind of program analysis. What if you first want to do some analysis to actually then decide on some kind of a rewriting step? Let's just say dead code elimination. You first analyze what is actually dead code.
Right. Okay. So you're absolutely right. We kind of don't really do program analysis. That's the kind of one of the entire points almost, to say we don't want kind of some compiler smarts in there, but we want to have like precise control for the user. But obviously, there might be cases where you might want to gain information, if you'd like, in a more general sense about what to apply, like where to apply. I think that goes maybe a little bit in the question that Justus asked on, can you describe certain, like, kind of a certain situation or something like this where you want to apply a rewrite? What we have explored with is to kind of automatically try to search for good compositions of strategies, if that makes sense. So you say like, oh, here's the bag of all the possible rewrites you can apply. Now try to apply these rewrites, and you do kind of a search-oriented automated process where you try to apply different optimizations, and then you see kind of, and you hope to find the good one or the best, right? This is now obviously formalization that really allows for something like this, right? So I have a way to encode kind of a sequence of a sequence of rewrites, how that could be applied, and like we want to explore kind of this fully automated, you don't do anything and we fully automatically apply all of the individual rewrites in a kind of search-based fashion, down to there's no search at all and it's all specified by a programmer, which is kind of more what the talk I gave today is kind of about. But we would be interesting to provide some middle ground, right? Where you say like, I give you precisely what a tiling strategy is or something like this, right? But I don't care where you apply it. Please find that out for myself, right? So I would like to have kind of an interaction between an automated system and programmers.
Mm-hmm. But how do you choose what is a better rewriting? Because you only have kind of either it fails or it succeeds. I mean, if it succeeds, how do you know that it's good rewriting?
Yeah, so I think it's quite often not really clear what better here actually means, right? So better, I mean, better for us means that it contributes to eventually leading us to good performance. But it's not always clear that a single rewrite step improves on any clear metric. So it's not clear that there is an easy to design kind of cost model that you could ask to say, well, if I do this rewrite step, will I improve or not, right? Sometimes you really want to make it worse before it gets better in whatever metrics you pick. And so for that, it's not necessarily clear how to design that. It might be that we look at like something like reinforcement learning or like some more kind of like machine learning driven aspects to tackle this. And on the other hand, it might be in certain domains or for certain hardware that you can actually design cost models, right? And that's obviously then a little bit up for how somebody might use this system that we are designing here.
Justus, you have a question.
Can't hear you. You have your mic.
Yeah. Sorry, I have to click so many buttons.
Yeah,
okay. Cool. So I kind of have two. One of them is, which you basically kind of talked about right now, is like, is it feasible to combine elevate with cost analysis, to basically say, I'm gonna like, I mean, if you have the type system like this, you can sort of even like encode it. You can say like, I have a rewrite strategy that relies on having cost information about the thing, and you have like sort of a previous traversal that calculates that, and you say, okay, well, if I find a thing that is has this amount of work in it, then I will do the rewrite, or I won't.
Yes, for sure. As in the sense of like, I mean, elevate on its own, right, is composing functions together. That's what it is at the core, right? What you then do with these functions. So if you essentially say, I only apply them as certain other conditions are true or not, is in some sense, at least so far, a little bit outside of the language, right? So it's like, here's your elevate strategy. It's a composition of individual rewrites. It might be the tiling strategy that might be a meaningful unit for you, right? And you could now decide to kind of build some external entity to say, oh, I do my program analysis, I make my decision, I have my cost model, and I apply it, okay? It might be interesting to see if we could, in some sense, bake these notions in, either at the type level that we now started to introduce, right, or potentially, well, I'm not entirely sure what it would mean at the language level other than at the type level, but it might be that you could annotate and say, you write over your arrow kind of some cost or whatever, or have like some mechanism to evaluate this. And then, well, I mean, then it's the question what do you actually do with this, right? Does this mean, I would have to think about what that would mean, right? But in some sense, kind of the observation is like that might be kind of the next layer on top of this foundational layer, which just talks about how you compose the rewrites together mechanically. Yeah.
And then the other, I guess, kind of short question I had was, I heard it at Splash again a talk about, but people talk about turning, arrays of structs into structured arrays, which it seems is still a thing that is important and good to do. So is this something that you could do with Elevate?
Yes. So I mean, turning multiple arrays into a struct is essentially just you zip them together, for example, like you take elements out of the two arrays, put them together, and now they are in a struct and you form an array around this. So I don't see a reason why we can't do stuff like that. Like Elevate and like Rise, the computational part, we have worked on this like for a couple of years now. That has kind of a wide range of now compiling for, CPU and GPU. That's kind of our two main targets. And particularly on the GPU, there are quite a lot of kind of GPU-specific memory optimizations, like coalescing memory accesses in certain ways, reordering them, and like something like struct to array, array of struct is one of the aspects that we have looked at in that setting as well. I think we are now particularly interested also like more specialized hardware stuff. So for example, like can we exploit the tensor cores on an NVIDIA GPU that can only do a matrix multiply in certain sizes, right? And we work with like colleagues in the US who design a new hardware architecture that can be reconfigured at runtime. It has certain specific optimizations, and we have like some interaction and ideas how to apply parts of this for that specialized hardware, and then like how you might re-optimize when you reconfigure and that sort of things, right? So I think this is kind of now here starting to build kind of foundations where we can start to play and apply. And I think for us, particularly this, you switch the hardware and you change your schedule, that I think is still the most appealing aspect for this, for a systems person, right? You write your domain specific program once, and then you swap out either automatically or manually your schedule or your strategy or whatever you call it. I think this is like something that a lot of people would like to have, but don't know how to design. So I think that's kind of the biggest quest, I guess, for us here.
Okay, cool.
Yeah, any other questions? Yeah, Michael, you probably saw or can see in the chat that a few people had to leave because of teaching.
That I expected something like that already. I mean, that's perfectly fine, obviously.
Yeah. So any other questions from anyone present here?
Who are you working with in the US, just out of curiosity?
Oh, so we are, as part of the University of Edinburgh, we are part of a DARPA project called Software-Defined Hardware, SDH. And we have, we do kind of the software side in Edinburgh, particularly the two main leads in this in Edinburgh, Michael O'Boyle and Mary Cole. And the colleagues in the US is the University of Michigan, who is designing the hardware component mainly, and then the University of Arizona, where they have people looking mainly in kind of algorithmic questions and graph algorithms and how to optimize them for this hardware and so on. So that's the project we collaborate there with.
Interesting. Cool. fun to see your. I mean, I've heard this talk before twice. If you recall, I was at Dresden before, and you were there twice.
Yes.
During my time, but it was kind of cool, like seeing where it went.
Yes.
The sort of newer.
I hope that there's more room still, particularly on the type stuff is kind of fairly new, and we just submitted this, but that would be, I think, an interesting. I think this what I like from a programming language or from a research side. This stuff here is for me kind of the most interesting part. I think if we could actually really use this and we give kind of by example programs and we synthesize transformations automatically or something like this. Like, I tell you,
I would assume, like, especially something like, struct array to struct is something that you could synthesize out of a type specification.
Yeah, I would like stuff like that. I might hope so, or that we have like certain, I don't know. I mean, even just for fun, you say like, oh, is this true or not? Let's try. Like, encode this and see if we can synthesize one, like a program specification for, like, in program transformations for it or not. I think that would be interesting for sure.
And I guess the hard part there is going to be figuring out, like, there's presumably several ways to synthesize the result. How do you sort of guide? What is a good synthesized program?
True, which, by the way, brings us to one other interesting aspect that we discovered while developing this Elevate, is that you can use Elevate to rewrite Elevate programs itself. Right, so you can do kind of meta rewriting. So you can, in some sense, you could think, for example, of like, oh, now I have my program transformation, but maybe it's very inefficient. Can I optimize my program transformation by rewriting, right? So can I rewrite my rewrites by applying and so on? I mean, there's like, at some point it gets a little bit mind-bending, but we have used that at least for debugging purposes to rewrite or to apply this ourselves to these programs. Just an interesting consequence out of the design. Yeah.
Yeah, I mean, it makes sense though, right? Like you want your program you want to write it as straightforwardly understandable as possible, and then, but that might not be the most efficient way.
One thing that I haven't mentioned just at the very end is that we are also working on implementing both, like these RISE language, like the computational language, and the Elevate language in the MLIR compiler framework, which is like a much more systems-oriented side. So we have already an implementation, which is kind of now in the Clang family of compilers. It's a new framework, like sponsored largely coming out of Google, to actually encode these functional bits in this like very heavy, like compiler systems-oriented framework, where we hopefully would find a lot more applications if we can get the Elevate design in there, right, for rewriting not just our types of programs, but also, for example, we might want to think about what would it mean in this setting to rewrite a TensorFlow graph, for example. That might be interesting questions for us to look at as well. Cool.
Yeah, I guess we probably have to get to an end here. I see lots of people have other things. I'm seriously due to another meeting as well, although I told them already I'd be late.
Sorry for keeping you then.
I'd rather be here,
Okay. Cool. Thanks very much for inviting me.
Well, thank you very much for coming this way, and I'm sorry we can't invite you for dinner and anything like that. Hopefully some other time there. I mean, I suppose you also stay in contact with Stefan or so, who suggested you to come here, and well, maybe then at some point we hear more about your types and where they are going. Yeah.
Very good.
Well, so thank you very much. Yeah.
Bye-bye.
All the best. Bye-bye. Have a good evening.
Same to you. Bye-bye.